In the last lecture, we described how to produce a finite section or compression of an infinite dimensional matrix representation of the Koopman operator U tilde. So this is the matrix representation, and then this compression or a finite section is obtained by restricting this U tilde to first n rows and columns corresponding to the first n functions in our basis functions, so span of f1 to fn. And so the key question in that we face with this finite section is, how are the eigenvalues of the finite section, so un tilde, eigenvalues of un tilde, related to the spectrum of the infinite dimensional operator U? And we talked about the fact that the spectrum of the infinite dimensional operator contains eigenvalues, but also has a part that's called continuous spectrum and residual spectrum. So let's go through an example in which the finite section methodology is actually very successful. So the map that we are going to consider is a translation on the circle S1. We encountered this map before, starting from a point Z on the circle. And you know that Z is on this unit circle. We multiply with e to the I omega, and to obtain Z prime, which clearly is another point on the unit circle. So this is just, if you think about how this map operates, you start from some point on the circle here, and you jump over there, and that the size of that jump is omega. So here it is in complex notation. And then the jth basis vector, or the library that we're going to choose, is going to be e to the ij theta, and we're going to choose positive j's. So these are obviously complex exponentials. So theta is going to be between 0 and 2 pi. And so now we're going to apply Koopman operator U to the basis function fj. That's composition of fj with t. And that composition is really e to the ij omega plus theta, which splits into e to the ij omega e to the ij theta. And that gives us e to the ij omega fj, because we started with fj, which was e to the ij theta. So now the kjth element of the matrix is obtained by just taking what we just got here and inner producting with fk. So right, that would be u fj fk. And this is true because the basis functions e to the ij theta are orthonormal, right? They are of unit norm, and the inner product of them is 1 or 0, depending on whether they are inner producted with itself or any other basis function. So we get ukj as this inner product. So when we take into account that ufj is just this, inner producting this with fk, fk is going to give us either 1 or 0. So we get delta kj e to the ij omega. So in other words, the only elements of the matrix that are non-zero are the diagonal elements, ukk, because in that case, delta kj, the Kronecker delta, is 1. Otherwise, it's 0. So we have basically a diagonal matrix for our representation of the Koopman operator, and on the diagonal, we have the eigenvalues, e to the I omega, e to the I 2 omega, because if you remember from previous calculations, the eigenfunctions of this dynamics are these with eigenvalues e to the ij omega fj. I mean, this is clear from this representation over here. So we have a diagonal here and then 0 of diagonal, and then it's almost pretty much immediately obvious that we get, you know, any finite section that we choose here, and we have chosen really j's only with positive j, so j is equal 1, 2, 3, but the same thing would be true with negative j's, because this system of functions requires positive and negative j's integers in order to provide the basis. But anyhow, whatever we choose for the first n, we are going to get just diagonal matrix, and that's going to be a perfect representation of the Koopman operator on that subspace. So in that case, clearly we are successful, and the distinguishing feature here is that in this case, the Koopman operator has point spectrum. Now, here is an example in which the finite section method fails. So this is another map on S1 given by z prime is z squared. All right, let me write a little bit there because this is actually a well-known chaotic map, right? So if we unwrap the circle onto zero to pi, 0 to pi, and we denote the diagonal here with this red line, and then we're gonna the map is gonna do something like this. So anytime I start from here, I jump over there, and I get bounce of the diagonal, jump down, bounce of the diagonal, jump up, bounce of the diagonal, jump up, bounce to the other side, and so on. When you project it down and look at its dynamics, this map is well known, and I mentioned it before. To have chaotic dynamics, in fact, the future iterations are going to densely fill this 0 to pi, so densely fill the circle. So this is actually a chaotic map. In complex notation, we have z prime is z squared. If you write z to be e to the I theta, then z prime is equal to e to the I 2 theta, which is exactly z squared. All right. So you see here theta goes to 2 theta. All right. And then we're modding this here to pi, but the complex notation already takes care of that part. So let me erase this for a second and then go back to our line of thinking. So what we are really interested in is this situation in which we choose the basis functions again, just like before in the previous example in which finite section worked perfectly, to be e to the ij theta, or theta between 0 and 2 pi. And now we apply the Koopman operator to the jth basis function by composition, we get e to the ij 2 theta. So theta went to 2 theta. And then we write f of theta as a sum over the basis functions. Now j's are in z, so they can be positive, negative integers, and 0. And then we write u f of theta is obtained as sum over z, but the CJs, the coefficients are the same here, but each e to the j theta goes to the e to the I 2j theta, right? As we just showed. And so if you think about the matrix representation of this, if you have CJs here, so let's just write them. We have these coefficients of f in some vector. And here I've chosen the functions in the finite section to be with j is equal to 1, 2, 3, 4, 5, up to n. So you have C1 here, C2, and so on to Cn. And I've also chosen n not to be even, so the last row are zeros. That's not as important. But the point is that if you take a look as to what sits in front of e to the I 2 theta, it's C1, right? Because that was in front of e to the I theta. And now, as I apply the Koopman operator to it, it shifted to e to the I 2 theta. Yeah. So that would give me a vector that begins, with C1 in front of, so it's 0 in front of e to the I theta, and then C1 is the coefficient in front of the I 2 theta, and now we go 0 in front of the I 3 theta, and then C2, and so on. And so the matrix has this shape. It has a lot of zeros in various odd rows, and then it has one subdiagonal ones in every second row. And so easy to see that this matrix here, the finite section matrix, has only 0 eigenvalues, right? Everything that exists that is non-zero is subdiagonal here. So it has only 0 eigenvalues of multiplicity n. But it is known that eigenvalues, that this map here has continuous spectrum, and it's actually on the unit circle itself. It's a measure-preserving map. These measure-preserving maps have the spectrum, whole spectrum of the Koopman operator on the unit circle. And so the finite section method fails spectacularly in this case of chaotic dynamics. So one has to be quite careful in adopting methods like finite section for numerical computation, because in the case of your dynamics being chaotic, the choice of the finite section, such as this one, will lead to a large dichotomy between the spectrum of the finite section and the spectrum of the Koopman operator itself. All right, so that's a bit of a warning, but let's talk about the cases in which we are successful, like in the first case that we presented, where the finite section can be in fact used to compute. And so what I'd like to do is show how one can estimate the coefficients ukj of the finite section from data. So let's say we have access to measurements of n orthogonal functions, f1 to fn, on m points on state space. And now we're going to assume, make an assumption. We're going to say that the underlying dynamics is ergodic. So intuitively, the dynamics has settled on some attractor and if it had a dissipative component. And now that attractor is sampled in time very, very uniformly. Like on the Lorentz, we are coming to all the different parts of attractor repeatedly. The rigorous definition of ergodicity is a system is ergodic for any invariant set if any invariant set satisfies that it's either of measure 1 or of measure measure 0 for this measure mu, which is an invariant measure. So in the case of dissipative systems, this would pertain to attractors, and the measure in question would be actually the measure on the attractor. This is often called or rather there is a type of measure that is called the physical measure on the attractor, right? So now we're assuming this ergodicity. So when time goes to infinity, we get sort of repeated cyclic behavior, maybe not coming back to the same point, but coming arbitrarily close to the point repeatedly over and over in time. And let's see how we can estimate from data the coefficients in the Koopman matrix, U tilde n. So we have a choice of functions. And in this case, I'm going to start with an orthogonal set. And then I'm assuming the dynamics is ergodic on some set M with respect to an invariant measure. So XLs are points on a trajectory on this set. And the statement says, for almost any initial condition, so for almost any trajectory, the UKJs can be estimated with this limit, or rather can be estimated with this finite sum. They're precisely the limit when M goes to infinity, the average of the products between the complex conjugate of the kth basis function and the next iterate of the jth, or the next value of the jth basis function. So this is clearly the Koopman operator acting on Fj multiplied with complex conjugate of k. If your basis functions are real, then no need for complex conjugates here. But in general, as I've shown in the previous examples, our basis of functions can be chosen to be complex functions. All right. So the proof of this is not very complicated as long as we reference a quote unquote big theorem, and that's the Birkhoff ergodic theorem proven about 100 years ago or so by Birkhoff at Harvard, who said that, if the system, who said that if you take time averages, think of this as basically a time average along the trajectory of a function, the function being Fk complex conjugate times Fj composed with T. So if you take an average of a function over a long time, then that time average is going to be equal to the space average, provided that the system is ergodic. Birkhoff really proved that the time averages exist, but then as a consequence, he proved that if ergodicity holds, then time averages are equal to spatial averages. And so UKJ, by our definition, was equal to this spatial average, the inner product of U acting on Fj multiplied with Fk complex conjugate. That's just the definition of complex inner product. Over the invariant measure mu, one should always remember that L2, the space of integrable functions, the first thing that you need to do when you're defining an inner product is tell us with respect to what are we integrating. And here we are integrating with respect to an invariant measure. It's actually quite an important point, because if you have an invariant measure that is 0 everywhere except on some attractor, then the only thing that this procedure and the finite section method can reveal is eigenfunctions that are, defined on the attractor, that are not trivial. They're not defined off attractor, maybe 0 on the attractor. So this is for attractors that have non-trivial. It's for eigenfunctions that if you're going for eigenfunctions from the finite sections, it's going to reveal the ones that are non-zero on the attractor. So it's quite an important point. I'll come back to it in some remarks after. But so the reason why the proof is simple is UKJ is this. So this average over invariant measure. But that last expression by Birkhoff ergodic theorem is equal to the time average of this function, which is Koopman operator acting on Fj multiplied with Fk complex conjugate, right? So that's equal to that. So UKJ is equal to that, which is exactly the statement of our theorem. This is just the rewriting saying that this is the evaluation of the function Fj on the next point in the trajectory, xl plus 1. So it's easy to obtain the coefficients in the Koopman matrix by this time averaging, taking just the finite number of steps m, and of course we could discuss the convergence. But one of the things that's important to discuss here is that we have chosen an inner product that allowed us to do sampling. We started with space L2 of functions. L2 is somewhat unusual space. It's actually a space of classes of functions, because functions can differ at sets of measures 0 and still be in the same class. But still, we were able to evaluate this coefficient from almost any trajectory, single trajectory. We need just one trajectory to evaluate the coefficients here. Now, of course, if you take one trajectory and it's converging to some attractor, and from some other initial condition to converge to another attractor, you are going to get two different Koopman matrices for these different basins of attraction, for sure, right? So a single trajectory is going to give you what happens in a single basin of attraction, provided you have some, attractor with a physical measure on it. But this is actually an important point that is often neglected in practice, and that is that when we do this time averaging, and in the next theorem, I'm going to show how that is done using just matrix calculations using Moore-Penrose inverse. But when we are doing this time averaging, what we are effectively saying is we want to compute the on-attractor functions. So the part with the dissipative eigenfunctions need to be discussed a little bit further. And in principle, you cannot get it from a single trajectory in general. I should say that there are elements of this that are really nice. We are sampling the functions on points in the state space and then take the limit m goes to infinity. So we are approximating the action of u, but we are also approximating the individual functions by their sample on m points. And so there is an element here of sampling, and if a sampling can be made to work, this kind of sampling even in high dimensional spaces without the curse of dimensionality. So that's not bad, actually. That's a nice feature. So let's see how that works in a second on the case of non-orthonormal basis. But here we have to remember that besides the basis vectors, we need the existence of dual basis vectors, like I've talked about in the previous lecture. When you have non-orthonormal basis, you have the basis vectors themselves, and then you have the associated dual as well. and the basis vectors and dual basis vectors satisfy the orthonormality conditions like this. So recall the infinite dimensional Koopman matrix coefficients should read, we get UKJ is UFJ inner producted with the dual vector FK hat, right? So you get these projections or coefficients by taking whatever function you're interested in. And if you want the projection on the jth basis, kth basis element, so this would be the kth coefficient, then you need to take the dual vector and inner product it. If you remember, in linear systems, we had this kind of a situation where we had these products of X and WJ, or rather I'll write it as WK. WK and then VK. This was a kind of a projection on the kth basis element using the dual vector WK. Something very similar here. The coefficient itself is the inner product between the function here and the dual element. All right, this is how we get the coefficients. Now that would again require us, this inner product is defined with respect to an invariant measure again. So that would require us to integrate something in potentially a very high dimensional space. And we don't want that. We want sampling. This is why this result is so potent, right? You take one trajectory, you sample along the trajectory, you get a data-driven expression for UKJ instead of integrating this potentially gnarly thing in high dimensions where you don't know either the invariant measure or how to really execute this integral if you're in 100 dimensions. So that's actually quite an important point. In principle, for computing this, you don't need to know anything about the invariant measure. Just run this and you get the correct result. So that's profound. All right, so now we have the coefficients. And we're gonna pick a finite set of independent functions and the associated dual set in the span of F tilde of our finite set of functions. F tilde here, that's a span of these functions. That's a finite dimensional vector space. In the finite dimensional vector space, these functions are independent, so they provide us with a basis. And then for every such basis, you can get a dual by just making sure that each of these functions, let's say G1 hat, is orthogonal to all the other functions, F2 to Fn. You can always do this, right? So you can always find a vector that's orthogonal to n-1 vector, n-1 vectors. So that's a hyperplane. You find a vector that's orthogonal to that. You find G1 hat, and then you proceed to find G2 hat, G3 hat, and Gn hat. All right. So now, by construction that I just described, the jth basis vector and the kth dual basis vector inner product to delta jk, to Kronecker delta. And these functions gk hat by construction are unique because they're each orthonormal to n-1 vectors, and F tilde, this finite space that we are constructing our finite section on. So you can think of these as library functions again. All right, so we'll split the space F, that's our big observable space, into F tilde and F tilde T. And we are going to define by this PF the orthogonal projection on F tilde. Okay, this in effect assumes the remaining basis functions are orthogonal to F tilde. It's kind of an important point to note. If you want to do skew projection, that's a different calculation, but this is what we are going to do here. And so write GK hat to be the projection of FK hat. Remember, FK hat was the dual basis vector. I have an infinite basis of fj's, and I found an infinite dual basis that has to exist. We are assuming it exists. I'm not saying it has to exist. That we are assuming that it exists in our space, and now we're gonna construct these GK hats as projections of FK hats. And the nice thing about this is that that those GK hats defined this way are precisely the dual vectors in the finite dimensional subspace F tilde. So they're exactly the ones that we need. So in other words, you can just work in a finite dimensional space, find the dual, and everything is fine. How do we prove this? We use the fact about projections that I didn't mention before. I think they're self-adjoint operators. So in an inner product, if you have this kind of an inner product that is equal to just applying PF to the first argument instead of the second, that means to be self-adjoint. And so since Fj is in the space F tilde, projecting Fj by PF gives me back Fj, because I'm in that subspace that I'm projecting on. So that gives me back that. And that is delta Jk. What did I just get? I get that inner product between Fj and this thing here is delta Jk. But earlier, I found Gk hats to be inner product with Fj and give my delta Jk. Since these guys, Gk's are unique, then Gk hat is exactly PF FK hat. So defining GK like this is exactly the correct thing to do, and kind of intuitively the correct thing. And so now the Kj coefficient here in the finite section are obtained as UFJ GK. If I replace GK hat from this with PF FK hat, and then self-adjointly push to this side, I see that this Kj element is really just the action of this projection, Koopman operator, projection acting on Fj. What did we define this to be? Well, we defined this to be precisely the compression or the finite section. So this coefficient that we're finding is precisely the element of the finite section in the basis F tilde. Okay, so how do we find those? Again, I don't need to do any integration. I don't need to find these projections, nothing like that. If I assume ergodicity, this theorem tells me, the assumptions are pretty much just like in the previous one. This theorem tells me that the coefficients are limit when m goes to infinity of the same kind of product like last time, except that instead of that Fk complex conjugate, now I have Gk hat complex conjugate. I have the dual vector in the finite dimensional subspace. And so look at this. So this is the same thing represented using the fact that T of XL is XL plus 1. That's my dynamics. XL plus 1 is T of XL. That's my nonlinear dynamics. This function here, so if I pull M inside to each element, so G hat CK divided by M are obtained as rows of this matrix. So this is conjugate or Hermitian transpose. So we complex conjugate and then transpose our matrix F. So this is F dagger, F inverse, F dagger, where F is what we're going to call the data matrix. And so the data matrix here, if you choose your library of functions, F1, F2 to Fn, you put those functions in rows, and then you evaluate them on this X. X is the column X is the column of points of the trajectory, so x1 to xm. So each column here contains evaluations of one function on m points along the trajectory. All right. So there are two things here. One is proving that ukj hat is exactly this. The other one is that, in fact, this part here can be computed. If you know the data matrix, this part divided by m can be computed precisely using this matrix operation. And that's nice. You see, in the previous case, when we had orthonormality, we had FKs and FJs. So knowing FKs and FJs was enough. Here, we don't have orthonormality. We would have to compute the dual vectors, but we are computing them, but we are computing it entirely using the data matrix. So here, for the first time, we are doing everything data-driven in this finite section domain. So this is the first thing in a numerical computation that you form. You form the data matrix. In this case, the rows are the functions. The columns are functions evaluated on points of the trajectory. All right, so let's prove this. So mu, again, is an invariant measure. And so we know this relationship. The Fj inner producted with the complex conjugate give us delta jk's, yes? But we also know from Birkhoff-Ergodic theorem that this integral here can be represented as the time average, yes? So this time average between the values of Fj and Fk hat, a complex conjugate, evaluated on a trajectory, gives us delta jk. But this matrix here, multiplied from the right by f, look at that, this is the inverse of this, also gives us the identity matrix. So this delta jk are components of the identity matrix. So this is n by n identity matrix. So what is in f? What is in f is the functions themselves, so these guys here. So when I multiply these functions that are organized, whose values on trajectory are organized as columns, with the row of this, what should be in a row is precisely the values of this guy here, the dual vector, because that divided by m gives us in this expression exactly delta jk, just like here. All right. So the rest of the proof, of course, how do you get this? Well, it's very similar, except that here, instead of fj, we replace it with ufj, and we are going to get that expression. But we also got to the point where we got to understand that the dual vectors can be obtained as rows. Well, dual vectors, these dual vectors here divided by m, can be obtained as rows of this matrix over here. So, as I mentioned, we call F the data matrix, and then this matrix F plus, which is F dagger, F inverse, F dagger is called the Moore-Penrose pseudo-inverse of F. The reason why it's called the pseudo-inverse is F, of course, does not have to be a square matrix. It has n components in this direction, m components in this direction. So the best we can do in that case is a pseudo-inverse. So if you multiply f from the left by this, you get identity. And that's the idea, that multiplying f by this gives identity. So if this was a square matrix, it would really multiply it from the left by f inverse. Analogously, but for a non-square matrix that doesn't exist, and so this is called the Moore-Penrose pseudo-inverse. All right, so now we have a new object, the approximation of the finite section. The finite section itself is obtained by this limit when components or components of the finite section, elements of the finite section, and find that at this limit when m goes to infinity. Now, if m is finite, then we'll put an a on top, and so this expression gives us f of tx multiplied by the Moore-Penrose pseudo-inverse. So this is just taking this really, but using it at a finite m, right? At a finite m, we are going to approximate these guys with, or rather, approximate these guys, yes, with f dagger, f inverse, f dagger, right? So the only difference here and in the formula that I have next is that fj's are evaluated at L+1 at the next point, right? So this is this f prime. So f of t of x, that's fx plus 1. That's denoted by f prime. So f prime is the data matrix at the next step. And the finite section is obtained as Moore-Penrose pseudo-inverse acting on f prime. Easy to code in MATLAB, in pretty much any numerical language you have out there. All right, so f prime is the value of our data matrix at the next point in time, and this fk is the column vector, just like before. So now, remember, we are interested, now we know how to compute the finite section. And we are interested in now computing approximations to eigenfunctions and eigenvalues. So let's start by assuming that there is an eigenfunction, eigenvalue pair, lambda and phi, such that phi is element of the span of f tilde. So it's really in the finite dimensional subspace. Then we have pf phi to be phi, because phi is in subspace. U phi is lambda phi by assumption, because phi is assumed to be an eigenfunction of u. And projection again gives us lambda phi. So the finite section, this is the finite section, acting on that phi, which is an eigenfunction, produces an eigenfunction again. So lambda will be in the spectrum of this finite section. So actually, more generally, an operator u and a projection p phi, that's what we use, that somehow what we proved here, that they commute, right? If you apply the u pf, as the same as applying pfu. So they commute. It is known that they commute if and only if f tilde is an invariant subspace of u. So when f tilde is an invariant subspace, the spectrum of the finite section is a subset of the spectrum of u. That's what we had in the first example, because we had an invariant subspace, and the spectrum that we found by finite section was exact. Now, an eigenfunction phi of u in f tilde, if it exists in f tilde, if it's in the span, can be obtained from an eigenvector of the finite section just by multiplying that eigenvector. That's a set of constants, right? Components in an n vector, and multiply that with a function. This notation really means a multiplication of a finite vector with a finite set of function, or a vector of whose components are functions. Or it can be also expanded as sum from k is equal 1 to n ak. So these are the components of a, fk, but fk's are functions. This vector a is supposed to be an eigenvector of un tilde. So it satisfies un a is lambda a, because for such a phi, then u phi is un tilde a dotted with f tilde. Yes. That's lambda A because A is an eigenvector of un tilde dotted with f tilde, and that A dot f tilde is exactly phi from here. So that's lambda phi. So un A equals to lambda A is equal to u phi is equal to lambda phi. And the dot notation I've just described. As I said before, the theorems that I gave are convenient because you use sampling along trajectories. You don't need to know invariant measure. You don't need to know these projections. You don't need to know the dual vectors. You just sample certain functions along trajectories and you construct a finite section representation. I should mention the space of functions L2 of mu is restricted because the resulting spectrum is going to be on the unit circle. I didn't prove that particular theorem, but that is true. If you have L2 with respect to mu, where mu is an invariant measure, then the spectrum of the Koopman operator is on the unit circle. So in general, you could choose a more general measure, nu, that has support in the basin of attraction, and you can use, points that weakly, when you increase the number of points, converge to the measure nu, and their images under the map, and you can construct a finite section which is valid for functions of attractor. The potential problem with this is the choice of space. So L2, if you look at square integral functions with some ambient measure nu, that might have a very, very large spectrum. So there is actually a construction that is much more adapted to the dynamics that you can do. I will talk about it in a future lecture that is specific to the context of dynamical systems. Very often in the literature, the measure nu is chosen as some arbitrary measure, and that can lead to some very serious, very serious problems in the interpretation of the results. So one needs to work a little bit harder. But if you notice, even for L2 of mu, you might have worries about, hey, now I'm computing some things with respect to invariant measure, I need to integrate. We found a way of sampling or finding the coefficients in the finite section just by sampling points along trajectories. So that's kind of the ideal way of doing things, that these theoretically we proved that that while it would be possible to find these coefficients using some invariant measure computation, you don't really need to do that. You can just use sampling.